Log on, tune in, find out. Another good idea from Cambridge.
Okay, so first of all, I'd like to say thank you to the organizers of the program for being here. Well, the Newton Institute is a very nice place and also a very good place to work. Okay, so now I'm going to go to the second part of this neuroscience model, nonlinear integrate and fire neurons. So since Jose has already given you the derivation of the models, I'll just write the equation directly. Remember that I'm looking for a function p of vt that represents the density of neurons at voltage v at time t. And we said there are two important quantities, that is V reset and V firing. So and we explained that when the voltage of the neuron reaches V fire, then immediately emits a spike, discharges, and go back to the voltage VR. Okay, to simplify the model, why don't we just translate this and put V fire equal to 0. So then the equation that the P satisfies is partial T P equals partial VB P plus the drift term that I'm going to write just minus V plus, sorry, I'm putting it on that side, so then this is plus minus P equal, minus n of t delta at the point V reset. And this equation is satisfied for V between minus infinity and 0. No, it's on the other side. Oh, sorry, plus. Yeah. Okay, what boundary conditions do we put? So for this P, we want decay at minus infinity. We want P at 0 is 0 because at the firing point there are no neurons, they immediately discharge. And then there is this quantity VR that is a negative in our model, where the function has a delta. The interpretation of this model is that whatever falls in at 0 reappears as a delta at VR. So whatever, that is a source term there. So then I put P at 0, 0, P at minus infinity, okay. Some decay we'll discuss later. Okay. And also mass conservation, the integral of P dV has to be 1. Okay, here you see there was a coefficient here in front of the diffusion term. I'm just taking it to be 1, and I'm going to be considering the case B less than 0 inhibitory. So if I'm going to study global existence, we'd better restrict to the case B less than 0 because for the positive case, Jose has explained that there is some finite blow-up. Okay, something else I didn't tell you who n is, but n is just the flux that falls in at time 0. So n of t is minus the derivative of the function at the point 0. Okay, so now let me tell you what the results are. Okay, and then we put some initial data, p sub initial data. Okay, so the results, and this is joint work with Jose Antonio. There is also myself. That is Maria Gualdani, who is also here. and that is also Maria Schombeck, or some combination of these four names. Okay, so we show local existence, and this is done through a fixed point argument. We also show global existence, through a fixed point argument plus uniform estimates. And then I'm going to make some comments on asymptotics. And let me say that this is work in progress, but even in the linear case, there are some surprising results there. Okay, so let's go to work. The first thing, I'm going to reduce this equation to something that I know how to handle, that is a Stefan problem. Because at the beginning we didn't know what to do with the equation. So the first idea, okay, this is a Fokker-Planck equation with some other terms. At least let's change a Fokker-Planck equation to a heat equation by the standard change of variables, y equals e to the tv, and tau unit time equals 1/2 e to the t minus 1. And consider our solution change from P to W. The equation that you obtain for W is a heat equation partial tau W equals partial YYW. So you got rid of the Fokker-Planck term, but you have the Vn term, the nonlinear one, partial y of W, and then you have the delta. Now, let me change the n to m. There is a relation. Let me call m to be the derivative of W with y, the flux, also at the origin. So then there is a simple relation between n and m, don't worry about it, plus m, and now your delta has moved position to y equals VR over alpha tau, where this alpha tau, don't worry too much about it, is just well, some function depending on time, very well behaved, so you can almost ignore it. And this, if I change n to m, you just get here p m alpha minus 1. Okay, so this is the equation satisfied about W. Again, W at 0 is 0 for all time, and decays at minus infinity. Okay, it's a heat equation, and then you have this first order term, and then the delta at another position. Okay. So now, let's try to kill this guy. And then, we change again variables again. This is just a standard change to kill the first order term, and say that your new space x equals y minus the integral between 0 and tau, the Vm alpha minus 1. So then, if you rename your u of x comma tau equals w of y tau, the equation that u satisfies is, okay, again heat, you then change this, equals heat diffusion, you've killed this term, but now here is the difference comes in here. Now for before the value y equals to 0, now it corresponds to some s of t, s of tau that depends on tau. So this means that you have a moving free boundary. And your value, y equals 3r over alpha of tau. Okay, whatever it is, I'm going to call it x equals s1 of tau. So the equation that you obtain is the following. Okay, now your delta goes at the position s1 tau, and m is the derivative of the minus the derivative of the function at the point, not at 0, but at the point x equals s of t, where this s of t is the point where the function vanishes. Okay, let me give you a little drawing. Then now your function vanishes at a point s of t that moves with time, and okay, at the point s1, the corresponding place where you have the delta. So this is your new u. And okay, this is a Stefan problem, because if I compute this is a Stefan type. Because if I compute the movement of the free boundary, s prime of t, just look up there the relation between x and y. So it's precisely dm alpha minus 1. And what was m? It was the flux across the free boundary. Across s of t. This tells you that free boundary is moving at the speed given by the flux. This is the Stefan condition. So if you didn't have the delta part, then that would be the true Stefan problem. Now you have the delta, you have to handle the delta, but you know how to solve the Stefan problem, so let's try to use that for this equation. Okay. So now the reference we are going to use for the Stefan problem are the papers by Friedman. There are some Russian books, but they're hard to read, and we'd better stick to Friedman. Now, let me give you some remarks on the equation. So I'm going to be using... Okay, guys, if you forgive me, let me rename the time to t. It's x, s1 of t. Okay, there you go. So that's our equation. Okay, the first remark is that we have conservation of mass. This was already pointed out by Jose, because this is, after all, P is a probability measure, so it preserves mass. The integral of P dv equals 0 between minus infinity and the free boundary. Sorry, now it's for u. U dx is equals to 1. Then we also have a jump condition, because we have the delta in that equation. So the function u is going to be continuous, but it's going to have a jump. The derivative is going to have a jump at the point s1. So I can say that derivative of u at the point s1 from the right minus the derivative at the point s1 from the left equals how much? The coefficient of the delta, m. Okay, minus m. On this notation, the jump of the delta, and what is m is just the derivative of the function at the point s of t. And then something else that is also important is notice that the free boundary S of t is increasing. And here is where the sign of v becomes important. Okay, maybe I forgot this minus in there. So if v is negative, then the speed of your free boundary is positive, because m was positive, then it's s is always an increasing function. So this agrees also with the Stefan problem. The case be positive, the Stefan problem already has blow up, so of course this one is going to have blow up. Okay. Now we can erase this and let me tell you how to solve the equation. No, before that, let me give you a relation to another equation that I was interested before. And this was a joint work with Lincoln Chase, myself, Maria Gualdani, and Imo Kim. So then the transformation, okay, let me not tell you what it is, but we had a density of people called buyers, a density of people called vendors, that they were trading on something, and this coordinate represented price, and this was the free boundary P of t. Okay, if you look only half of the problem, okay, the equation that the f's satisfies heat equation plus a delta. Okay, there is a coefficient here that is exactly the m, P of t minus a. Maybe I should use s of t here, s of t minus a. So it was a model, if you only look at half of it, is whatever flux of people comes in here, reappears here, it's a source. So if you only look at half of the model, it seems exactly the same. Now the difficulty is in how the free boundary moves. In this model, the free boundary moves depending on the second derivative of the function. While for the Stefan model, the movement of the free boundary only depends on the flux that is the first derivative of the function across the free boundary. So this second derivative here makes things much more complicated. But on the other hand, both models have a lot of similarities. Anyway, that is said, let me go to the results. So for the results, I'm going to use an integral formulation of the problem. So, okay, first thing I'm going to define, let be the Green's function for the heat equation in R. I'm going to put already the four arguments, x, t, c tau, is okay, some constant, 4 pi t minus tau, the exponential minus x minus c squared over t minus tau, and there is a 4 here. Okay, using this Green's function, you can give an explicit solution to the problem. Now, because you have the delta, you will have some extra terms appear, but just take the Green identity. Okay, partial c of g partial c the u minus u partial c the g minus partial tau gu equals 0, integrated in two regions. The first region is going to be before the delta, 0 less than tau less than t, and the second region integrate after the delta up to the free boundary s of t. Okay, if you integrate, you add both equations, what you get is that your solution of the problem can be written as the integral from minus infinity up to s of 0 of g x t c0, the initial beta at c with c, minus, okay, I'll write it here, the integral between 0 and t m tau g x t comma s of tau tau tau. This is why transparencies are useful, but I'll do it on the blackboard. M of tau g x t is 1 of tau tau d tau. Okay, now let's understand what you get. So the first part here is just the solution of an homogeneous heat equation with initial data ui. So this is just heat with initial ui. Nothing special, very good. Now, the second part is what takes care of the free boundary. So this one is the one that makes that u at s of t to be 0. While the third part is the one that takes care of the delta at the point S1. So if you understand what the three parts mean, then it's going to be easy to handle them. Okay, I'm not going to erase this because you have here the equation. I'll erase it here. So once you have this Duhamel type formula, you can easily do a fixed point argument. Now, here we have u, here we have m, that was the flux of u across the free boundary. Let's write an equation for m that is going to be much simpler. So I remind you that m was minus the derivative of the u at the free boundary. Okay, so take this formula, differentiate with respect to x, and evaluate at the free boundary s of t. See what you get. Okay, let's put a derivative in here. You can put a derivative here, or because this is after all a convolution, I'll put the derivative here. So I end up having, I would get something like this. And evaluate s of t, t, c, 0, ui prime, dc. Now, let's go to the second term. Okay, let's go first to the third term. Okay, this one isn't too much of a problem. You just throw in the derivative in this guy and evaluate. So for the third term, you get minus twice the integral m of tau dx so t is 1 of tau tau d tau. Now, the problem is when you differentiate in this part, because when it's not enough to just throw in an x in here, because when t equals to tau, s of t equals to s tau, then this is going to have some trouble. So it's going to give you a delta after all. So when you differentiate this, you have to be very careful. I'll just read on the side that the way to when you take this limit, the integral from 0 to t m of tau dx of xt s of tau tau. Okay, you can throw the derivative x in here. Now you evaluate an st. You have to be careful, and this is giving you 1/2 mt plus okay, the integral what t m of tau dx t s of t s of tau. So you are getting, when you differentiate this thing, because when x t equals to tau, you are going to have some trouble, then this extra term appears. So then you need to combine all those terms, and you are going to get, there is a 2 here, then there is this term here, s of t s of tau t tau, and the other one that we had, and you see where all these 2's appear. So just forget about this. This is just a technical thing. And now we have a closed expression for m. So let me call all these things t of m. We are seeking a solution of m equals to t of m. Then we are going to find a fixed point for this operator t. If this t is a contraction, then we are done. Now, if you find m, it is clear. Well, no, I'll see that later. Only the formula for the Green's function. Well, now let me just have a quick look at the Green's function. When your arguments in space are far away, let's say that this quantity is bounded from below, then this exponential is a very good one, and it's going to help you in the computation. Your risk is when t goes to tau and these 2 arguments are close by. That's your risk that you need to avoid. So once you have that, once you understand that, let's see how far things can go. Okay, so now let's do the fixed point argument. Let me fix the space. I'm going to fix the norm of m to be the supremum of m of t, where t is in between 0 and some prefix sigma. And I'm going to define C of sigma to be the space of functions that are continuous in 0 sigma, and that its uniform norm is bounded by m. So now a proposition is that the application T that I defined before in this space goes to the same space, y además, and moreover, that's Spanish, T is a contraction. Then with this, of course, there is a fixed point. So this m is a solution of this equation, and that's why once you have your m, you can put it back in the equation, and there exists u for time t between 0 and sigma. So short time existence will fall automatically. Then for long time we have to do uniform estimates, but let's do it later. Let me just give you a quick idea of why this formula is true. And what's the risk? I mean, what can go wrong for long-time existence? Okay. So, okay, bien, bless you. Bien, I'm going to choose it as constant times 1 plus the supremum of the derivative of the initial data. And then sigma is going to be a quantity that depends on m small enough. Now let's see how to show that if we start with a good m, then we finish in another good space. So let me show this. But it's easy, just look at this formula. So the first part, the way we chose n takes care of this, and this is the Green's function for the heat, well, the fundamental solution of the heat equation. You can, I mean, don't worry, you can get it bounded. This is not giving you any problem. Now, the difficult part is to estimate these two things here. And here is where the movement of the free boundary is crucial, because as I said, when t goes to tau, s of t goes to s tau, then this object becomes very dangerous and you lose your estimate. But you have a precise way to estimate the difference between st and s tau. So just st minus s tau is the integral between tau and t. Remember, the free boundary was increasing. And then, okay, you have some quantities here, dm alpha minus 1, don't worry. And since we are starting with things that start with bounded norm by m, this is less or equal than m and the difference between t minus tau. So somehow you have a very good control of the difference of these two. When you put it in the formula for the g, then you can work out a little bit the estimates, and then you are done. And then for the third part, what happens? You have st here and s12 here. Okay, this term is even much better than this one, because if s of t was here, s of tau was here, because the s is increasing, and s1 of tau, by definition, is always at a positive distance given by the absolute v of vr, etc. The position of the delta is always some fixed, some distance behind, so you can control the distance. The distance of these two is bounded from below, and then you can handle the g is helping you to estimate. So if you play around with the g doing some estimates with those exponentials, you can check that this is true. Now the computation that t is a contraction is more complicated, but it follows the same lines. And then you see how you get local existence. Now, okay, let me erase this formula, but we'll be using it all the time. Let's see what happens for global existence. Okay, you have proved short-time existence for some time sigma small enough, and this sigma depends on m, and m depends on the norm of the derivative of the initial data. So if you try to restart to see if you get global existence, Why is it go wrong? Why can it go wrong? Because of the derivative of the function. If this quantity blows up, then you may not be able to continue. But then you show the following proposition: is that there exists mu positive. Okay, it's going to be small, but who cares? Such that for all time t0, if at a position u of x x t0 minus mu is finite, then you can get that the supremum of the nt when t is in between t0 minus mu and t0 and t0 is finite. And this mu is independent of t0. So if you have your derivative bound up to time t0 minus mu, then you can always extend some quantity mu where you have, okay, this is the flux, but this is what you need. With this you can show that actually the derivative of x is going to be bounded for a little bit longer time, and because mu is uniform, that you can continue up to infinity and you get global existence. And the way to prove this is, okay, again, take the Duhamel's formula for m and play around with the estimates. And okay, don't worry, I'm not going to write that on the blackboard. I just did the easy one. Okay, so I will finish this talk with some comments on the asymptotics, long-time asymptotics. So as Jose has mentioned, this thing will have exponential decay to equilibrium, and since asymptotics, since I'm looking at V negative, this thing is going to have a unique equilibrium. And we expect exponential decay to the equilibrium. Okay, but the case b less than 0 is nonlinear, and it's a little bit more complicated. Let's start with the linear case b equals to 0. Let me write the equation. Now, for the asymptotics, it's better if we go back to the original model and not the model with the free boundary. So the original model was for t equals p of t equals pdv plus the Fokker-Planck part, dpli plus n and the delta at the point br. Then t at 0 is 0, and n was the flux across the 0. But there is no nonlinearity here. So this is a linear operator. I don't need this anymore. Let's find the spectrum. And hopefully that will tell us something about the decay. How much time do I have?
Let's say 5 minutes, maybe a bit of follow.
Okay, imagine that you don't have this term. This is a Fokker-Planck equation. Okay, let's find the spectrum of this guy. First, for the Fokker-Planck equation, this is a well-known computation. Take Fourier transform plus C partial Cp. Now this is an equation p hat. This is an ODE for p hat that you can solve, and it gives you that p hat equals constant times Let's find the spectrum of the operator. So let me call this L of V, and let's find the spectrum of P. The spectrum. So I'm looking for solutions of this equation. So for each lambda, your P lambda can be written of this form. Now, because this is going to give you some troubles at the origin, you need to split between, you can put two constants. This is for positive C, and this is for negative C. If you Fourier back, you obtain the corresponding eigenvalue for eigenfunction for the eigenvalue lambda. Now we need to check what are the miscible values for this lambda. So then it turns out that the only lambdas that you can find are the spectrum for the Fokker-Planck. Let me write it in the space L to X, functions with exponential tail at minus infinity. It's just the natural numbers, and okay, the origin that gives you the stationary state. So this is well understood. And eigenfunctions can be written and have this form when you Fourier back is a well-known Hermite polynomials. I shouldn't have erased this. So let me just tell you how to compute the spectrum of our operator LP to be PVB plus Fokker-Planck PV PP plus N delta at the point BR. Okay. This is only telling you that you are going to look for solutions to lambda where you split in two parts. P1 lambda if V is between minus infinity and VR, and P2 lambda if V belongs to VR 0. What is this? Okay. I'm almost done, don't worry. So, if you are far from the delta position, this is a Fokker-Planck equation, so you know all the only possible solutions. They are the ones I have found before with that form. Now, what happens? Because of the delta, I may have different functions on each side. I just have to make sure that your your P lambda is continuous across the delta, but the delta forces to have some kind of jump. So if I put a P lambda 1 here and a P2 lambda there, okay, let's with some constants, okay, and here I'm oversimplifying things, but just think about it. I'm putting the eigenfunctions that are known here, here, and then I try to match them. Well, one of the surprising results is that if I consider the space L to M, that is the space of functions with decay and with polynomial decay, 1 plus x squared to the n f squared, then your spectrum, okay, I didn't write the spectrum for the Fokker-Planck in this case, but it's the same one, is the set of complex numbers such that the real part of lambda is less than 1/2 minus n, and then, okay, the stationary state that we know, but you see the eigenvalues have disappeared. It has only continuous spectrum. Now take n goes to infinity in L2 with exponential decay at the tails, then the spectrum, and this is very funny, it's just 0. So this is an example of an operator of an almost empty spectrum, and the zero is the equilibrium point that we are not, you can give an explicit formula, Jose did it in his talk, but the spectrum is empty, so surprising. So what happens about asymptotic decay to equilibrium? Aunque there is no spectral gap, for L, but L produces a semigroup. So what's happening? The thing is that sometimes the decay of the semigroup is related to the spectral gap, but sometimes it doesn't. So if the spectrum is empty, you may still have a spectral gap for the semigroup, and Josep showed asymptotic decay, and if we want to find the precise constant to have exponential decay to equilibrium, then we have to show it directly. So let me say that asymptotic decay for the semigroup also, or for our solution, must be studied directly. So we are always use that the spectrum of the linear operator gives you the spectral gap and the decay rate for the solution, but here there is one example in which you have to work in another way, and I think this is the end of my talk.
Questions or comments? Okay. If there are no questions, then we can comment afterwards, and thank you for your talk.